Hey team, welcome to week 3. We are almost to a halfway point of Calc as far as our online portion of things go. So you guys have been doing so awesome. I know that it's super tough to do it online like this, but I'm so proud of what you've gotten done so far, and we're doing good. Feel good about what we've gotten done so far. So we are about to do one of the tougher parts of what we have to do online. So brace yourself for what we're about to do. If you need anything, if you need help, if you want to Zoom, if we need to do a group Zoom, we can do a group Zoom. Whatever we need to do, we can do to get you through this. But know that once this week's done, we're kind of on the downhill slide. So there's a cute little picture of me. I'm pretty sure that's what I look like at my desk most of the time. That's how I felt over the last week, checking my email 3,000 times a day. But, here we go. So this week we are going to talk about two main things. And the first one isn't so bad. We're going to talk about the fundamental theorem of calculus. Sounds important because it is. The fundamental theorem of calculus says if f is continuous over a closed interval AB, and capital F is any antiderivative of f on AB, then the integral from a to b of f of x dx is the antiderivative at b minus the antiderivative at a. So essentially, last week we talked about closed integrals. This is kind of the shortcut. The fundamental theorem of calculus says we just plug b into the antiderivative, plug a into the antiderivative, and subtract. You always do the top one minus the bottom one. So we are going to try some. We're going to try 4 examples with this, and then we're going to talk about a cool thing that we can do with it, and then we'll move on to the super tough stuff. So our first example, letter A, we want the integral from pi to 0, well, from 0 to pi, of cosine x dx. So the first thing we're going to do is just find the antiderivative of cosine, which is sine, from 0 to pi. And so then that just means I'm going to plug in pi, and I'm going to plug in 0, and I'm going to subtract. So sine of pi minus sine of 0. Well, I know sine of pi is 0. I know sine of 0 is also 0. So that's 0 minus 0, and final answer is 0. Not too bad. Let's try B. B wants the antiderivative, the integral, from negative pi over 4 to 0 of secant x tangent x dx. So first I want to know, what is the antiderivative of secant x tangent x? Well, I know that that has to be secant of x, because the derivative of secant is secant tangent. But I still have to worry about my 0 and my negative pi over 4. So I'm going to plug in 0, I'm going to plug in negative pi over 4, and then I'm going to subtract. So secant of 0 minus secant of negative pi over 4. So what I'm going to do is I'm going to use my unit circle, and I'm going to say, okay, the cosine of 0 is 1, and if I flip 1 upside down, that's still 1, right? Negative pi over 4 means I'm going to go backwards. I'm going to go down pi over 4, so that's the same thing as 11 pi over 4. I look at my cosine. Cosine of that would be square root of 2 over 2, and we flip that upside down, which would be 2 over the square root of 2. Rationalize it out, your 2's cancel. It's just square root of 2. So I get 1 minus the square root of 2. Can't simplify that. That's it. That's my answer. 1 minus the square root of 2. Letter C. It's getting a little bit trickier. The integral from 1 to 4 of 3/2 square root of x, which we might think of as x to the 1/2, minus 4 over x squared, which we might think of as x to the negative 2. So I'm just going to look at this part first. I know that that would be x to the 3/2, right? It'd be like x to the 1/2 plus 1, which would be 3/2, over 3/2. Well, 3/2 over 3/2 would cancel. Okay, x to the negative 2, I would add 1 to that. That'd be negative 1. That's why it's over x. And then I'd put that -1 out front. That's why it's positive. So now I have x to the 3/2 plus 4 over x. I'm going to plug in 4. I'm going to plug in 1. So I have 4 to the 3/2 plus 4 over 4 minus 1 to the 3/2 plus 4 over 1. That's like the square root of 4, which is 2, cubed, which is 8. That'd be 1. And I'm going to distribute that 1 to those things. So that's 8, that's 1, that's 1, and that's 4. But when I distribute my negative, it's going to be a -4. So those ones cancel. So my answer is 4. Last one. So if I have dx over x plus 1, that's like 1 over x plus 1 dx. That tells me I've got an ln of x plus 1. So I plug in 1, I plug in 0. So 1 plus 1, that's ln 2. 0 plus 1, that's ln 1. ln 2 is a big gross decimal. If you try to put it in your calculator, it's going to be nasty. ln 1, if you put that in your calculator, is 0. So ln 2 minus 0 is just ln 2. So hopefully you kind of see how those work. Hopefully you're comfortable with finding antiderivatives at this point, and really it's just a matter of plugging in numbers for you. Fun fact, if we want to find the area between some equation, the graph of an equation, and the x-axis from an interval AB, so like two x values AB, first you've got to find the zeros of your function. Find your x-intercepts. Any of your x-intercepts that are between your A and your B become subdivisions. So like A to 1, 0, and then 0 to B. Whatever your x-intercepts might be that fall between that A and B. And then you integrate over each of those subintervals, and then you add the absolute value of those integrals together. So if they're negative, you make them positive, add them together. So let's look at an example of this. We want to find the area of the region between the x-axis and the graph of f of x equals x cubed minus x squared minus 2x from -1 to 2. So that means my A value is -1, my B value is 2. So step 1, we want to subdivide -1 and 2 at the zeros of this. So we set that equation equal to 0. X cubed minus x squared minus 2x equals 0. If we can solve this by factoring, that's the best way to subdivide. So if I can factor that, I see they all have an x in common. So I take out x, and then I have x squared minus x minus 2. If I can factor that, even better. Factors of -2 that make -1 are -2 and +1. And then you set each factor equal to 0, and you get this x equals 0, x minus 2 equals 0 gives me x is 2, x plus 1 equals 0, x is -1. Well, I already have -1 and 2 as my A and B, so 0 is where I'm going to subdivide. So I'm going to find the integral from -1 to 0, and then from 0 to 2. So my first subinterval is -1 to 0. I'm going to integrate x cubed minus x squared minus 2x. So x cubed is going to be x to the 4th over 4, or 1/4 x to the 4th, however you want to think of that, minus x to the 3rd over 3, minus 2x squared over 2. Those 2's are obviously going to cancel, but I wanted to make sure you knew what was going on. I'm going to plug in -1. So when I plug in -1, that's +1 over 4, minus, that's going to be a -1, so that'll be plus 1/3. Those 2's cancel. -1 squared is 1, so -1. 1/4 plus 1/3 minus 1 is -5/12. So that's my first answer. But that's only one subinterval. That was -1 to 0. Now I need to do 0 to 2. Well, we already found the integral. X to the 4th over 4 minus x cubed over 3. We know those 2's cancel. That's just x squared. But now I want to go from 0 to 2. So I plug in 2, and I get 16 over 4, 8 over 3, and 4, and 0 is just going to zero out, so I don't have to worry about it. So that's 4 minus 8/3 minus 4 is just negative 8/3. So that's step 2. Step 2 is where all the main work is. Step 3 says, okay, take your two answers, take their absolute values, so we're going to make them both positive, and add them together. So 5/12 plus 8/3 gives me an answer of 37/12. So the area between this curve from -1 to 2 and the x-axis is 37/12. That's how you do those area problems. And I know there's one on your homework because I put one on there. So that's how you do the fundamental theorem of calculus. Anytime you have numbers with your integral sign, you do top minus bottom. All right, on to the good stuff. When you have indefinite integrals, we talked about these a little bit a week or two ago, that's when you don't have numbers. These are the ones where you do plus c. Anytime you don't have numbers, you don't have little bounds on your integral, you always put a plus c with your answer. We are going to talk about the substitution method with these. And this is where integrals get real nasty. Substitution method is just the backward chain rule. Barf. So what we have to do on these is, it's when it's going to be too gross to like multiply out or work out, but we're going to do a substitution to solve it. So if you look at this example, I want to find the integral of x cubed plus x to the 5th times 3x squared plus 1 dx. I don't want to take this to the 5th power. I don't want to multiply this times itself 5 times and then multiply it times 3x squared plus 1 so that I can integrate it. That's disgusting. So what I'm going to do instead is I'm going to make a substitution with a letter u, the soldier boy u. So I'm going to let u be my inside function. This one is pretty simple and straightforward, but this one's to the 5th power. So I'm going to say, okay, what's going to the 5th power? X cubed plus x, that's my u. But then I have to find the derivative of that. That's my du, derivative of u. So that would be 3x squared plus 1, and then we put dx because that's the derivative of x. So 3x squared plus 1 dx, that should look familiar to you because it's right there. So my original integral is the same as the integral of u to the 5th because I replaced x cubed plus x with u. And then this whole thing, this 3x squared plus 1 dx, is the same thing as du. We decided over here. That is a lot easier to integrate. So I go ahead and integrate that. I say, okay, u to the 5th. I add 1 to my exponent. That's u to the 6th over 6 plus c. Done. Except that's not my final answer because I want to know what the integral of this is, not what the integral with u's are. But I know that u is x cubed plus x, so I plug that back in. Where I see u, I put in x cubed plus x to the 6th over 6 plus c, and that's it. I'm done. Answer found. So that's how that substitution works. You want to find what's happening, make the inside stuff u, find the derivative, replace it, and then solve it out. So let's try some more. We're going to do a couple more here. So this one, we have the integral of the square root of 2x plus 1 dx. So I'm going to let u be my inside stuff, 2x plus 1. The derivative of that would just be 2 dx. But if I look in my problem, I don't have a 2, right? That means I have to put a 2 in. So in order to put a 2 inside, I have to put a 1/2 outside because 1/2 times 2 is 1, and it keeps it the same. So I can say, okay, there's a 1/2 hanging out outside to cancel out that 2 that I need inside. So now I can say, okay, that 2 dx is just my du now. So now u to the 1/2 is u to the 3/2 over 3/2. 1/2 still chilling outside. 3/2 is going to become a 2/3 when I skip, flip, and multiply that up to the top. Those 2's cancel. I can replace u with 2x plus 1. And my final answer is 1/3 times 2x plus 1 to the 3/2. And don't forget your plus c anytime there's no numbers. Let's try another one. Secant squared of 5x plus 1 times 5 dx. So I can see the 5x plus 1 is my inside. That's going to be my u. So du is 5 dx. Oh, how handy. It's right there. So I have secant squared u du. So I'm going to integrate secant squared. I know that's tangent of u plus c. And then I just replace my u with 5x plus 1. And there's my answer. Tangent of 5x plus 1 plus c. All right. So those weren't too bad. Anytime you need to add something in, this would look better if I replaced that with a du. That was skipping a step on that's my bad. Otherwise, if it's there, you just replace. So let's do one last super tough one. We have the integral of x times square root of 2x plus 1 dx. My inside stuff is 2x plus 1. That's going to be my u. That means du is 2 dx. Okay, well, when I look at this, I'm missing the 2. That means I'm going to put a 1/2 out front. But I also have this x just hanging out here. That's a problem, right? There's no x anywhere in here. So what I'm going to have to do is figure out what x is in terms of u. So I'm going to take this equation right here, and I'm going to subtract 1 and divide by 2. So x is 1/2 times u minus 1. Okay, so I just solved that u equation, got the x by itself. So now I know that x right there I can replace with 1/2 times u minus 1. So x is 1/2 u minus 1. And then this square root of 2x plus 1 is just my u to the 1/2 power, because a square root is a 1/2. And then to get a 2 dx, I have to put a 1/2 to cancel the 2 du. That's a lot. So now we're just going to make this look prettier. I have a 1/2 and a 1/2. That's going to be a 1/4 that I can just put out front so I don't have to deal with it. U minus 1 and u to the 1/2. So I can distribute u to the 1/2 in to make my life a little easier. That's like u to the first power. So 1 plus 1/2 is 3/2. And then 1 times u to the 1/2 is u to the 1/2. And now I'm ready to integrate. 1/4, chilling out front. U to the 3/2, add 1 to that, that's 5/2. U to the 1/2, add 1 to that, that's 3/2. Skip, flip, and multiply. So that's going to be 2/5 u to the 5/2, 2/3 u to the 3/2. Distribute your 1/4 in. That's 1/10 because 2 and 4 cancel. 2 times 5 is 10. 1/4 times 2/3. 2 and 4 cancel. 2 times 3 is 6. And we're almost done. But now we need to replace u with 2x plus 1. So final answer, 1/10 times 2x plus 1 to the 5/2 minus 1/6 times 2x plus 1 to the 3/2. And don't forget your plus c. Whew, that was a lot. So these can take a lot of time. Just be really careful. There's a lot going on with those. So that's it. That's all we're doing this week. Nothing too wild, nothing too crazy. You are ready for week 3 homework. Next week, we're going to do one last section from Unit 5, and we're going to do the Unit 5 test. And after this, we're going to do 3 more weeks. The last week, I'm just leaving open for you to catch up on anything you need to. So we have 4 more weeks left of online work, but we're only going to do 3 more weeks of actual stuff. That last week's just going to be your last test and finishing stuff up. So If you need anything, let me know. Make sure that you're trying to keep up. Don't fall too far behind. Most of you are doing an awesome job. I'm so proud of you guys. So hit me up if you need help, if you just want to email, if you want a video chat, if we need to do like a little class-wide Zoom session, I'm cool with that too. Just let me know what you need. I am here for you. Good work. Do your best. You got this.